Welcome to part 3 of the bare bones tutorial for LinuxCNC. In this lesson I'm going to be covering the STEPCONF wizard, and we're going to be setting up a Gecko Drive G540 to run our machine off of a parallel port. So to get started, we'll go to our Applications menu, and under CNC, we'll go to our STEPCONF wizard. The PNCConf wizard is the wizard that we use to set up Ethernet-based hardware, such as a Mesa 7i76E or a Mesa 7i96 or something like that. So inside of the STEPCONF wizard, we have three options. We can create a new configuration, we can modify existing configurations that were created with the STEPCONF wizard, or we can import a mock XML file. The import mock XML file will do its best to convert the XML data from Mach 3 over to information that the STEPCONF wizard can understand. At the bottom we have three options. Create a desktop shortcut to the configuration files, which is this little shortcut here. Create a desktop launcher to start LinuxCNC with the configuration, which is this icon here. The other option that it gives us is to create a simulated hardware configuration. And this is useful for making a configuration that is close to what you are trying to run for your machine, and then test out the environment. Once you get all of the little nuances set up, then you can go back, uncheck this, just keep hitting forward through the rest of the configuration, and all of the configuration settings that you made will stay, except for it'll get rid of the simulated stuff that works in the background. This is useful for creating multiple simulations for, well, in my case for tutorials, but it's also useful for creating a simulated hardware environment where you can test out HAL configurations, you can test out ladder setups, things like that. You can build your Glade or PyVCP control panels and test those out with the virtual pins and whatnot. And you don't have to be connected to physical hardware, which is a nice little touch. So from here we'll press forward. On the next screen we have the machine name that we're going to give it, and we'll call this test mill. If you put a space and say test mill here, the folder will automatically put in a little underscore. The axis configuration, we have a handful of choices. We have XYZ for a 3-axis mill, XYZA for a 4-axis mill. So if you wanted to put a rotary table on your vertical milling machine, it would create the A-axis for you to have the rotary table in place. We have XZ for a lathe configuration, an XYUV for a foam cutter machine, and we have an XY special. The most popular being the XYZ and the XZ. The default machine units, we have either inch or metric. The driver type, if we look inside of this list here, there's a list of popular drive types. And on the LinuxCNC website, if you look up drive types or drivers or something like that, you'll get the full list of tested and configured driver boards that users have submitted for their configurations, and they tell you the little breakdown of all of the step time, step space, direction hold, and direction setup. If you select one from here, in our case a Gecko G540, this will blank itself out. We can't change that because the settings are already stored within this configuration setup. Underneath here, we have the choice of one parallel port or two parallel ports. So if we had two parallel ports on our machine, we could configure both parallel ports for extended I/O. So we could have our Gecko G540 on one parallel port, and we can have a second I/O board on parallel port number 2, supplying additional I/O. The base period maximum jitter is the number that we get from our test jitter window here. Remember, I said in the first video, run this test, abuse the machine, go to your favorite website, do everything you can to bog down the machine, and then that base thread number, maximum jitter, we put into this little box here. If your base period jitter is over 50,000, it will automatically default itself to 50,000, and then you'll have to go into your INI file and make it higher. But remember, I said a 50,000 base period for a parallel port is not so good because it reduces your max step rate, and you'll have issues with rapid traverse and things like that. The machine will not run as quickly as it could with a machine with a better base period jitter latency. So we'll just stick with the default 15,000 for now, and we'll press forward. Now on the parallel port 1 screen, it sets up our step and direction properly. It sets up our spindle clockwise pin, Spindle PWM pin, amplifier enable, e-stop out, and then these are our inputs. If we look up the configuration for a Gecko G540, we'll see right here that it's pretty much set up properly. There are a couple of things that we do have to change. Pin 15 is going to be our e-stop in. Pin 1 is just a standard output, so we can use that for coolant pump. We can use that for an enable signal. We can use it for a digital output, for just driving a solid state relay to do something. Our X, Y, Z, and A are all automatically configured for the Gecko G540. If the motors are running in the opposite direction, just click on these invert pins if you want to change the direction of the way that the motor spins in the plus and minus directions. Our pin 14 is actually our PWM signal, so we'll set that to Spindle PWM. Pin 16 is our charge pump. And then pin 10, 11, 12, and 13 are our inputs, and we can use those for homing switches, limit switches, probe input, things like that. So we can set up pin 10 for all limits and home. We could set up pin 13 for probe in. And then if we wanted to set up a different input for something, we could always choose that as well. We also have 4 digital inputs that we can assign here as well. Again, for secondary type inputs that may not have a name here, but we know that we could utilize those in the future, so we could just turn those on. From there, we'll click forward. On the options screen, we have 2 choices for our graphic interface. We have the Axis screen, which is the default screen that LinuxCNC comes with. And then we have the Gmo. 'K. 'Pi. 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 ' first and second video. We have a selection for an on-screen prompt for a manual tool change. So if you have a machine that only has a single tool spindle, or if you do not have an ATC, you would just check this and it'll prompt you with a little window and it'll say, please put in tool number, whatever. We have this include HAL UI user interface component, and we'll always make sure to check that. And what that does is it just loads in some additional user interface components that we can use in the future when we try to link buttons for PlayStation controllers or physical inputs and outputs, things like that. If you watch my HAL tutorial series, you'll see how we can utilize the HAL UI user interface. We also have an option for including the PyVCP GUI panel. We won't get too far into that. We also have the option for including classic ladder PLC. And if we wanted to write PLC logic for our machine configuration, we could also include that. I do have a tutorial series on classic ladder as well. From there, we also have this window that allows us to put in some preparatory MDI commands. But we'll just skip over that for the time being because we just want to set up a basic machine. Now we'll get into setting up our axes. The first question it asks you is your motor steps per revolution. It defaults to a couple of different settings, 200 being the most common stepper motor that's available on the market these days. The next option is driver microstepping. The Gecko G540 is a 10 microstep driver. The other drivers that you'll buy online, your lead shines and your stepper motor onlines and things like that, those have selectable microsteppings on the actual driver board itself. So depending on your dip switch settings on the driver board, you would set up the driver microstepping according to that. Just be aware that the more microsteps you produce, the slower the motor will be ultimately. So there's a little bit of a trade-off between speed and accuracy. If you're driving your axes with a 1-to-1 ratio, so the motor being directly coupled to a ball screw, you don't have to worry about gear reduction. But if you're using, for example, a CNC router parts rack and pinion drive that utilizes a 3-to-1 reduction ratio on each of the rack and pinion drive units, so you'd put the ratio right in here. If you're dealing with a lead screw, your lead screw pitch is going to be in revolutions per inch. The most common lead screw these days is either the 1605, the 1610, or the 2005 or the 2010. The first two numbers being the diameter in millimeter, and the second two numbers being the pitch. So a 1605 and a 2005 will have the same pitch. They have a 5 millimeter per revolution pitch, but they have a different outer diameter, being 16 millimeter or 20 millimeter. Here it's asking us for the lead screw pitch for revolutions per inch. So we have to do a little bit of math here to get ourselves the number that we're going to need. So what I'll do is I'll load my calculator. And we know that we're dealing with a 5 millimeter pitch ball screw, which is 5 millimeters per revolution. We have to convert that to a decimal inch value. So we'll use number 5. And then we'll divide that by the number constant 25.4, which is the amount of millimeters that are in an inch. There are two number constants when dealing with inch to metric conversions. There's 25.4 and there's 0.03937. You can multiply by 0.03937, or you can divide by 25.4, and you'll get a very similar result. There is a little bit of error in 0.03937, so just be aware of that. So we divide by 25.4, and we get this number here, 0.19685. We then divide 1 into that pitch, and we result in 5.08 revolutions per inch. So in our lead screw pitch, we'll put that value. Our maximum velocity is our maximum rapid and jog feed rates, and that is in inches per second. Most machines are done in inches per minute. So 1 inch per second is actually 60 inches a minute. So we'll leave this at 1 for right now, and that'll give us a good starting point. The same thing with the 30 inch per second acceleration. These are good numbers to start off with. If you want to have a slower acceleration, you'll have a higher number in your maximum acceleration. So if you want the axes to wind up a little bit more before they reach their maximum rapid rate, you can use 75, you can use 100, use 200. Just be aware that the higher the number, the longer it's going to take for the motor to accelerate to its maximum speed. The next options that we have are our home location, our table travel, home switch location, home search velocity, and the home latch direction. So our home location, typically industry term would be zero your machine. And when you zero your machine, the machine searches for its home position switch. Once it makes contact with the position switch, it backs off of it slightly, and it sets that as your machine 0 point. In this case, we'll make it easy. We'll leave this at 0. You could actually override it and say that when it touches that location, it's at a different number than 0, but 0 is usually the most common. Our table travel is going to be in either positive or negative values based on the axis travel of our machine and where our home switch is located. So if our home switch is in the X positive direction, our table travel will be in the negative direction, and if our table travel, or if our table home is in the negative direction, our table travel will be in the positive direction. For the time being, we could just leave these numbers the way they are. The home switch location, much like the home location, is where the physical switch is located inside the machine. If we say that the home switch location is 0 and the home location is 0, then it's just going to find that position and call it 0. The home search velocity is just the feed rate that the machine will search for its home position with, and we'll leave that at 0.05 for the time being. The home latch direction means that once it reaches the switch position and triggers the switch, when it's set to same, that means that it touches the switch and it'll search for the switch in the same direction that it touches it in, basically. If you set it to opposite, it will touch the switch and then back away in the opposite direction until the switch is no longer making contact. And I find that that's the better way to do it, but it's all personal preference, really. There's also a test this axis button here that we can use to enable the motor, set our velocity, acceleration, and set a test area. We can jog the machine around with these buttons here. We can test our positive and direction for our motors. We can set up a test area to run the motor back and forth with a certain amount of stroke range. I personally don't use this, but it's here if you want to use it. So for our y-axis, it's just more of the same stuff. Same thing for our z. You'll see here that the table travel in z shows a -4 and a 0 position for this table travel, because z-axis home is typically in the positive direction away from your table. So it defaults to a negative value here, whereas the other axes, they think that they're homing in the negative direction, so they have positive soft limit values. If you just had a home switch, not a homing and limit switch, set up in the center of the stroke of your machine, in the case of like an X2 or an X3 mini mill or a Grizzly 0704 or whatever it is, you can set up a home switch in the center of your table travel so that when the machine homes, your scale lines up with the center of your machine. And in that case, you would put a negative number in the first box and positive number in the second box, because then you would have table travel in both directions. And what this is setting up software soft limits. So the table will not go more than 8 inches in one direction and 8 inches in the other direction for a total of 16 inches. So now we have those all set up. The Gecko G540 comes with a Spindle PWM. And if you've set up Spindle PWM before on Mach, it's very similar. You set your PWM rate for, I have a Super PID spindle controller for my router, which runs at a 50 hertz frequency. And we can say that our speed 1, which is our low limit speed, is 0. And we'll say PWM 1 is 0. And then our maximum speed is 30,000 RPM with a PWM of 1. And if we needed to make changes to any of these values, we could always reopen the STEPCONF wizard and we could change these values here and then test out the new configuration without actually having to go in and modify the actual HAL file or the INI file that get generated after the STEPCONF wizard is complete. Because I selected that it's a simulated environment, this little error message comes up here, or this little notification message comes up here, that this is a simulator only and it will not run hardware. But like I said, we could always reopen and modify this configuration file, and we can go in and uncheck that box, keep pressing forward, and it will make a physical hardware configuration for us. So press done. It says configuration has been built and saved. Do you want to quit? We select yes. And now here we have the two icons that we wanted to create. One of them will launch our simulated environment using the Gmokapi user interface. In the other folder, it'll create all the files that we're going to need for our LinuxCNC configuration. So that concludes the lesson on the STEPCONF wizard. I hope you found it helpful. If you have any additional questions, feel free to drop them into the comments below. As always, please be sure to like and subscribe if you haven't already. And stay tuned for the next video. I'm going to be covering the PNC-Conf wizard, and then we'll get into the actual nitty-gritty of what these files do. So again, thank you for watching, and we will see you soon.